Hi, I'm Steve Hallday, and this is our third video in the series on bare metal programming for Raspberry Pi. In the second video, we built a simple kernel as simple as possible, which was just a single instruction infinite loop using machine language. Now, admittedly, this was a little bit boring. We couldn't really see what was happening or couldn't tell if we'd even built it correctly, to be honest. This time we'll do something a little bit more exciting. We'll try and do something that we can actually see. If we take a look at our Raspberry Pi board again, we notice down here there's an LED that lights up when we apply power to the board. And right next to it is another LED labeled ACT. This is the LED that we're going to be interested in for our next exercise. What we're going to do is try and get this thing to blink. Now, it doesn't sound like much, but at least it's something we can see it doing. And as we've learned, just about anything you do in machine language can be a little bit tedious. To prepare for our machine language exercise, what we're going to do is study a little bit about computer architecture, and we'll explore what makes our Raspberry Pi work. The Raspberry Pi architecture is based on what's known as a von Neumann architecture. Von Neumann was a guy that built one of the early computers, and he established an architecture with different components, and as a result, most of the computers that we program today are of this ilk. The von Neumann architecture in the Raspberry Pi has three different areas in it. The CPU, which we know as the processor, memory, which we sometimes refer to as RAM, random access memory, and then peripherals. These peripherals are internal peripherals, not necessarily printers and things like that, but peripherals that would be on the SoC, on the system on a chip. Let's first take a look at the memory. The memory is really just a big array of bytes. They start at an address of 0 and they continue on down until we get up to 512 megabytes, which actually is 536,807,911 in address. So because of the 0 gives us another one of these. We've got 536,870,912 bytes of memory on a Raspberry Pi. The peripherals, as we talked about, these are actually internal peripherals. For example, we've talked about the graphics processor. That's a peripheral on the chip. The UART it stands for Universal Asynchronous Receiver Transmitter. It's used for communicating with the serial port. The timer is a peripheral, so we can tell the timer to count off so much time for us and so forth. So we have these different peripherals. These are all in the same silicon in the system on the chip. So they're not actually part of the processor itself, but they are part of the same chip. And then we have a system bus, which allows the processor to talk to memory, and the processor can also talk to the peripherals as well. The processor consists of several components. In the top left, we have the ALU, which stands for Arithmetic Logic Unit. The ALU takes care of any addition and subtraction or any bitwise ANDing and ORing types of operations. The ALU operates on general registers, as we see in the top right. These general registers are like very fast memory inside the processor itself. The ARM processor is what we call a load and store machine, which means that the ALU only operates on the registers themselves. Any data that needs to be stored out to memory, the control unit moves the data between memory and the registers. The ARM processor has 16 registers. We number them 0 through 15. And these are considered general purpose registers. We can do pretty much any operation we want with any of these. However, the three highest registers have some special meaning. Register 15 is the program counter. What that means is this register contains the address and memory of the next instruction that we want to execute. Register 14 is the link register. The link register holds the return address when we call a subroutine. So when we call a subroutine, the program counter basically gets stored in the link register. Register 13 is a stack pointer. Stack is a section of memory over here that will hold various values, parameters, transient data. And so the stack pointer points to the top of the stack here. If we want to add things to the stack, if we push things on the stack, then the stack pointer will increase to show the new top of the stack. And as we pop values from the stack pointer will decrement as well. We talked about the control unit a little bit. One of its jobs is to take data from memory and put it into the registers. Another thing that the control unit will do is figure out how to configure the various pieces of hardware within the processor so that an instruction may be executed. This brings us to the special registers. There are several different special registers within the ARM processor. I'm not going to go through all of them here. I'll go through just enough to kind of give us an idea of what's going on. One of the special registers is what we call the instruction register. The control unit uses the program counter to find the next instruction to execute and then takes that instruction, loads it into the instruction register. That's called the fetch cycle. And then it decodes that instruction inside the instruction register, which means the control unit sets up the ALU and so forth, all the circuitry to be able to actually perform the instruction. And then the control unit causes the execute cycle to happen where the actual instruction is executed. Another special register inside this special registers section is what we call the CPSR register. CPSR stands for Current Processor Status Register. This special register allows us to understand what's been happening in the processor and also to control to some extent the operation of the processor. It consists of these four parts: the flags, status, extension, and control bytes. The status and extension bytes aren't really used in the ARM processor in the Raspberry Pi. The flag byte has several bits. Each bit represents a different flag that allow us to understand what's going on in the processor. These two bits here aren't used currently. The N bit represents a negative flag, which means that the last operation resulted in a value that was negative. The 0 bit works similarly. It tells you if the previous operation resulted in a value that was 0. The carry flag is for unsigned operations. When the unsigned operation results in a value that's too large to store in the register, the carry flag will be set. The overflow flag is for signed operations. It serves a similar purpose for signed operations. If the signed operation results in a negative value when it should have been positive, or a positive value when it should have been negative, then the overflow flag will be set. The Q flag is for what we call saturated arithmetic. What this means is if I add two numbers, and for example, if I were dealing with 8-bit values and I added two numbers and they would have resulted in a value greater than 256, then it would cap the value at 256. So for saturation types of arithmetic, the Q flag gets set if the value in the previous operation resulted in a saturated value. And as I said, these X bits aren't being used. The J bit is if the processor is in Giselle mode, which means actually that the processor can execute Java bytecode directly, although I haven't played with this, so I'm not too familiar with it. The control bits down here represent some different ways that we can control how the processor operates. If the I bit is set, then that disables interrupts. If the F bit is set, it disables the fast interrupts. If the T bit is set, then the processor is operating in thumb state. Thumb state is kind of an interesting state where the operations, instead of taking 32 bits, only take 16 bits. So we can store more operations in a smaller amount of space. And then the mode here, the processor actually can run in any of these different modes. Mode basically means that the instructions have access to certain types of capabilities within the processor. And so you'll see that there's a user mode, a fast interrupt mode, I guess you'd call it a slow interrupt mode, supervisor mode, abort mode, undefined mode, and a system mode. So these are the current modes defined in the processor right now. The last topic I'd like to touch on in our architectural discussion is what's called the instruction pipeline. Processors don't execute instructions in one atomic step any longer, but they actually use phases in their execution. Here I'm showing 3 phases. The first phase being the fetch phase. In the fetch phase, the control unit in the processor would grab the instruction from memory and load it into the instruction register. In the decode phase, the control unit would configure all the hardware within the processor to actually perform the instruction, and then during the execute phase, the processor would compute the results from the operation. Here I'm showing 3 different instructions, and what happens with the pipeline is that when we start executing instruction 1, we fetch it into the instruction register. Then while we're decoding instruction 1, we can start to fetch instruction 2. And then while we're executing instruction 1 and decoding instruction 2, we can actually start to fetch instruction 3. You can imagine this causes some complexities. For example, if we hit a branch instruction, this may cause the pipeline to be flushed, and so we would have to start reloading the pipeline again. This would slow down the processing a little bit. And for example, you recall in our previous video where we had a branch instruction, we had to put a -2 in there instead of just a -1, and I said it had to do with the pipeline. Well, what happens here is when we are executing the actual branch instruction, the program counter is pointing at a couple instructions away from where we currently are. And so that's why we have to subtract 2 places from the program counter instead of just 1. This brings us to the end of our architectural discussion for Raspberry Pi. In our next video, we'll be discussing the instruction set for the ARM processor. Hopefully this will prepare us to write our machine language program to blink the LED. Also, I've set up an email account. If you have questions, you can email them to me and I'll try to include them in future videos. The email address is somePiGuy, that's P-I, not P-I-E, somePiGuy@gmail.com. I look forward to discussing the instruction set in our next video.